So we have discussed about a problem on pipelining. We are very uh, well-known problem in a pipelining concept. Now we will move forward for a different type of situation that can happen. You see one thing in previous classes, the strategy of pipeline that we have seen with respect to the reservation table was pretty straightforward. We have considered that each and every stage takes same amount of time for every instruction, for example one clock cycle only, and it's going smoothly. You see fetch, decode, execute, write back, and similarly when decode is running, fetch is running above this fetch of instruction 2, again fetch, decode, execute, write back, similarly for instruction 3, 4, 5 and so on. But in practical life, in practical situation, the execution of the instructions in a pipelining is not so straightforward, not so linear. There are several reasons for this, and we will discuss about the reasons and their solutions, how we can improve this. We will see, day by day we will gather knowledge over there. So we will start with a very simple problem, a practical situation, that is the idea that we are considering each and every stage takes same amount of time to for all the instructions is not fully correct in in practical situation. The reason is that if you assume that you have various say you have various instructions, you can have load instruction, load data to a memory, you can have add instruction, you can have subtraction instruction, you can have multiplication instruction, you can have division instruction and many more. Now among these, if you compare between addition and subtraction with multiplication and division, we know that multiplication is uh, basically successive additions and division is basically successive subtraction. So that means naturally it may happen that this addition and subtraction instruction take lesser amount of time than multiplication and division type of instruction, right? So if this happens, that means maybe the execution of addition will take say 1 clock cycle, but execution of multiplication will take say 3 clock cycle. It may happen, a very common situation, right? In that case, how the pipeline will behave? Let's try to analyze this. So let's take a situation that you have 5 instructions, suppose I1 followed by I2 followed by I3, I4 and I5, and among these 5 instructions assume that this I2 is a suppose say multiplication instructions, okay, and this is addition instruction. Okay, this is a normal instruction and this is addition instruction. Now why I am doing this? Because we are assuming that this instruction take 1 clock cycle to execute. This instruction multiplication, since I2 is multiplication, it will take 3 clock cycle to execute. It's, you see, I am only concerned for the execution stage, not for the other stages. I am assuming that for other stages it takes same amount of time for all the instructions. Okay, so this is a common instruction again, so let's take only 1 clock cycle. Again it is addition instruction, something say bigger, for example say 2 clock cycle, and this is again 1 clock cycle. So suppose situation is something like this. Now if I assume that how the reservation table will look like, So if we draw the reservation table in this consideration, let's draw it first. Fetch, decode, execute, write back. As simple as that. You know this. So let me draw the reservation table first, then I will explain. And this is clock cycle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Suppose let's take only up to 14, then if required we will see later. And the situation is something like, we will start with fetch 1, and then after completion of fetch I will start decoding the instruction 1, and obviously fetch 2 will start at that moment. Now after decoding instruction 1, again I will start executing instruction 1. Then after executing instruction 1, you see execution of the instruction 1 will take 1 clock cycle. This is all about execution stage. Okay, so that means write back of instruction 1 will start. Up to this is okay. I mean decoding of instruction 2 will start here. Fetch of instruction 3 will start here. Um, and this one execution of instruction 2 will start. At that time decode of instruction 3 will start, and fetch of instruction 4 will start. Right. Now, and I can easily say that this instruction 1 will come out from the pipelining because write back has done. But you see, as we have seen that I2 is the multiplication instruction and it takes 3 clock cycles to execute. That means this E3 will not complete at 4th clock cycle. 4, 5, 6. These 3 clock cycles are required to complete the execution of instruction 2. So E2 will continue, right? So when E2 continues, that means execution of E3 cannot be started at that moment. If the execution of E3 cannot be started, that means the third instruction is holded on the decode stage because the decode stage cannot pass its result to the execution stage at that moment. That means it will hold, the third instruction will hold the decode stage. When it is holding the decode stage, what will happen? Naturally, the fourth instruction that has been already fetched is not possible to transfer to decode stage because decode stage is already holding instruction 3, the previous instruction. So if the fetch stage cannot release the instruction 4 after fetching, fetch stage will not free for fetching the next instruction I5. So what will happen? It just looks something like a traffic jam. You have a road, lot of cars running one by one in a queue, and suddenly one car has a breakdown. And what will happen? If there is no way to bypass that car, all the cars will stop. I mean, after that, one after another. A similar situation is happening over here. You see that execution is running. That's why execution of E3 cannot be start over here. After 6 clock cycle, when write back of instruction 2 will start, then instruction 3 can start executing. And at that time, decode of instruction 4 can start. And at the same time, the fetch of instruction 5 can start. Right. So that means, and maybe after this E3 will take only one clock cycle, that is fine. Then W3 will start. It will come out from pipe. It will come out from pipe. And when when the execution of third instruction completed, then execution of instruction 4 starts, and decode of instruction 5 will start. And maybe instruction 6 if present, then instruction 6 fetch will start, and so on. But you see again, I4 is addition instruction which is taking 2 clock cycles to complete. That means E4 will continue for 2 clock cycles. That means E5 cannot start it. E5 will start when it will come for write back stage. And then only D6 will start, and so on, right? So if you closely watch the reservation table, how it will look like? We see we have something blank entry in the reservation table which was not present during the first assumption, because we consider the situation is very smooth. There is no dependency and all. There is no difference between the time to execute the different instruction in a particular stage. And technically, these entries, if you closely watch a particular stage throughout time, for example only the fetch stage. So if you consider this particular stage with respect to time is something like a pipe, or maybe throughout the in a particular time, if you consider the status of the pipelining, we can say, for example, the fetch stage, or maybe decode, or maybe execute, or maybe write back. We have something, a blank entry in the pipe, as if something is flowing throughout the pipe, and in between that one, we have something what we call, we can say something we call bubble, or technically this is what we call stall. So technically we say that the pipeline has stalled. Technically we say the pipeline has stalled. If the pipeline has stalled, then what will happen? So basically what actually you are doing? You can say that you are basically wasting the 5th and 6th clock cycle for working that fetch stage, or maybe decode stage, and so on. So if you waste the clock cycle, what is the result for this? We lose the efficiency of the pipeline. And if we lose the efficiency, the computer system will get slower. Now my question is that what is the task as an engineer, as a computer engineer? Somehow our task is to resolve the or you can say remove the bubble as much as possible from the pipeline. Now to do this, we have to learn a concept what we call pipeline hazard. And what is the pipeline hazard? Pipeline hazard, in only one line if I say, a, a strong reason of stalling. So we have to understand this pipeline hazard, what are the different situations for which this pipeline hazard happens and how we can remove this by various hardware and software techniques. So the detail of the pipeline hazard we will start from the next class.